respond well, or if the plating is very sparse, then it could take like up to 25. It could take many runs. So in order to demonstrate that this estradiol is acting through estrogen receptors, we actually did the same experiment, and we blocked the estrogen receptor with ICI 182-780. So again, with the astrocytes normally would respond with a calcium increase, but if you block the estrogen receptor, the response is attenuated. So this demonstrates that it acts on the estrogen receptor. So then we wanted to see what the dose response was for progesterone production. We actually did more concentrations at either end, but I just wanted to show the main points. So at 0.5 nanomolars, there's no significant progesterone production. At 0.75 nanomolars, there's an increase, but it's not statistically significant. Then by 1 nanomolar, there's actually maximal progesterone production. And then if we did 10, 100, and 1,000 nanomolars, and pretty much the progesterone response was the same. So this tells us that there's a very narrow window of estradiol that will stimulate progesterone synthesis. So even though the calcium starts a little bit earlier to go up, there may be a threshold value, and there's a very small window. So this is also consistent with a possible positive feedback mechanism, where the estrogen increases and there's no progesterone for an LH surge, and then when it gets close to the peak, around 1 nanomolar, then you also have a lot of progesterone, and this can allow for positive estrogen feedback. Also of significance, these were incubated for 60 minutes, but we wanted to see if this was a genomic versus a non-genomic response. So we figured if it's a fast response, it's most likely sleeping through a membrane estrogen receptor and not a genomic response with transcription and translation. Therefore, we took the same cultures and we treated only for 5 minutes with 1 nanomolar of estradiol, and again, we see that there's pretty much already a maximal response, and the controls here are very, very slow in producing progesterone.
Okay. You just do that by blocking transcription, and then you know, rather than the rapid time frame, because 60 minutes is also pretty short for a transcriptional event.
Yeah, but some people were complaining that it may be a little long, so we just did 5 minutes. But that's another way definitely of doing it is to block transcription. But we didn't do it. We just did a 5 minute really rapid. And then we wanted to demonstrate if the signaling mechanism is similar to neurons, and that the estrogen receptor will signal through a glutamate receptor, specifically mGluR1A, so type 1A. And LY367385 is an antagonist for the mGluR1A. So again, if we do this experiment and then we perfuse with the blocker first and then give a dose of estradiol, we see that the calcium response is attenuated. So this tells us that the signaling mechanism involves mGluR1A. Then we wanted to also demonstrate this with our progesterone assay. And again, controls and the antagonist didn't increase progesterone. The estradiol gave a maximal response, but then we pre-incubated with LY for half an hour and then gave both together, and that blocked the response, the progesterone response. Again, signaling through that the mGluR1A is involved. So now that we know that mGluR1A is involved, we wanted to see what would happen if we just stimulated the glutamate receptor without estradiol. So we tried to do a dose response curve at 1 to 10 nanomolars, and there was no significant calcium increase. By 100 nanomolars, there was a significant increase, but it wasn't very high. Then the literature reported that DHPG, which is the mGluR1A agonist, at 50 micromolars gives a maximal response in hypothalamic astrocytes for calcium imaging. So therefore, when we did that, we got a pretty high response, and actually it was quite interesting that it was actually the same response that we would get with 1 nanomole of estradiol. So these two are very similar. Then we thought, what would happen if we activated both receptors together? So we used both with a maximum dose, and we got even a higher response. And then we thought, well, does the estradiol change the conformation of the glutamate receptor? So when estradiol binds the estrogen receptor on the membrane, does it change the conformation and allow better signaling through the glutamate receptor? So we used a lower dose of DHPG with this estradiol, and again, it was almost the same. So you can actually now use a less dose of DHPG with the estradiol and still get maximal signaling. Does that make sense? So then, again, we repeated the study.
Can I go back to the last slide? Looks like it's more than additive effect, right? Because if you look at your 1 nanomolar and where's your 100?
This one? And this
100, yeah, 100, and, no, it's less than, no, it's more, it's not additive, it's partial, so.
Yeah, it's just
Might suggest
additive.
a similar mechanism.
Yeah, we think that it may change the glutamate receptor and signal a little bit better, like maybe a slight
Yeah,
confirmation
yeah,
change
but
or
it's
something.
probably through the same
Right,
mechanism.
right. So in our progesterone assay, we wanted to also see if what would happen with the glutamate receptor. So with DHPG at 100 nanomoles, there was no significant increase in progesterone. And with estradiol, again, we had a progesterone production. But now with both together, it was a much, much higher response of progesterone production. So this tells us that the hypothalamic astrocytes react to estradiol and increase calcium and progesterone. However, when there's surrounding neuronal activity, and glutamate is a very common excitatory neurotransmitter, when there's surrounding neuronal activity, it can actually influence astrocytes. So with the estrogen and now with glutamate from surrounding neurons, you actually get a much higher calcium response and a much higher progesterone production.
So when you combine the calcium with the progesterone data under the same treatment conditions, it suggests that it's not a linear relationship between calcium levels and progesterone levels, right?
Right,
Because-
exactly.
Okay.
Yeah. So we actually think that there's some certain threshold that you have to get a certain amount of calcium in order to trigger the progesterone. So at the lower doses of the estrogen, there's calcium that's increasing, but it's not high enough just to emit any progesterone. So that's why the progesterone is very shifted to a very narrow range. So the summary of findings to this point: estradiol stimulates a rapid elevation of the cytoplasmic calcium and progesterone synthesis in female hypothalamic astrocytes, and membrane estrogen receptor signaling requires metabotropic glutamate receptor type 1A. Next, I'm going to talk about several different types of proposed membrane-associated estrogen receptors. Again, the first evidence was from the 1960s, where there was a very rapid response to estradiol in terms of electrophysiology studies. So the most common proposed estrogen receptors on the membrane are estrogen receptor alpha and estrogen receptor beta, and these are the same estrogen receptors as the classical nuclear receptor, estrogen receptor alpha and beta. And then we believe that these signals through the metabotropic glutamate receptors, and I showed you some data already. Then there's other proposals. There's GPR30. This is a G-coupled protein receptor, very popular in the breast cancer literature, but also exists in other organ systems and other cell types. And these cells which lack estrogen receptor alpha and beta, they have GPR30 and they can still respond to estradiol. However, the membrane location of these receptors is quite controversial, and I'll talk about that a little bit more later. There's STX binding protein. So STX is a selective estrogen receptor modulator, and this binding protein will react to STX as well as estradiol. It's also G protein coupled, and it responds by activating phospholipase AC. However, the actual structure of this receptor is not yet identified. It's not characterized yet. They do have activity in estrogen receptor alpha and beta double knockouts, and is antagonized by ICI 182-780, so it has some pharmacology similar to the classical estrogen receptors. And lastly, there's estrogen receptor X. ERX has estrogen receptor alpha sequence homology, but it's only been reported in early development, like postnatal day 7 mice, and after ischemic brain injury in adult. And so what's unique about ERX is that although it can be activated by estrogen receptor, it can be activated by 17-beta estradiol, it's actually preferentially activated by 17-alpha estradiol. In addition, it's not antagonized by ICI